Hello students, in the previous class we have seen estimating the degradation function. There are three principal ways to estimate the degradation function that are the estimation for degradation function for the use in the image restoration process. The first one is estimation by image observation, and the second one is estimation by experimentation, and the third one is mathematical modeling. So in the previous class we have already seen how we estimate by image observation and experimentation. In today's class we'll see estimation by modeling. Degradation modeling has been used for many years because of its efforts, whatever it has done in the image restoration problems. And now the equation, it is image. Let us assume that an approach in modeling is to derive the mathematical model starting from the basic principles. Now let us see the procedure by treating in some details the case in which an image has been blurred by using linear motion between the image and the sensor during the image acquisition. Suppose that, let us assume that image is represented by f of x comma y. F of x comma y, let us take it as an image undergone under plane motion, and that x naught of t, this is x naught of t, and y naught of t are the time varying components of the motion in x and y direction respectively. Now the total exposure at any point of the recording medium is obtained by integrating the instantaneous exposure over the time t during which the image system shutter is open. Assuming that the shutter opening and closing takes place instantaneously, then the optical imaging process is perfect, isolates the effect of image motion. Then if t, capital T, this t is the duration of the exposure, then g of x comma y is equal to integration. So it is exposed from 0 to, for the time period t, therefore 0 to t f of x minus x naught of t comma y minus y naught of t dt, where g of x comma y is the blurred image. So applying the undergoing motion, you'll get the blurred image. Now from the above, in the above, we know that g of u comma v is double integration minus infinity to plus infinity g of x comma y e raised to minus j 2 pi ux plus vy dx dy. Now substituting the previous equation in place of this equation g of x comma y. Now here, in place here, we get this one. Remaining terms are as it is. Now rearranging the terms, reversing the integration order, we get 0 to t integration minus infinity to plus infinity f of x minus x naught comma y minus y naught e raised to minus j 2 pi ux plus uv dx dy dt. The terms inside the outer or whatever the terms are there in the Fourier transforms are displaced by the function. Whatever the terms inside the bracket, this bracket are there, are replaced by the function f of x comma minus x minus x naught of t y minus y naught of t. Then we get g of u comma v is equal to integral 0 to f of u comma v e raised to minus j pi 2 pi f of u x naught of t plus y v of y naught of t dt. Then taking, since this is f of u comma v, this is not independent on t, therefore we'll take out constant. So we take outside 0 to t e raised to minus j 2 pi u or x naught of t by y. This is like thing but transfer function. So g of u comma v is nothing but f of u comma v multiplied with h of u comma v. Now h of u comma where h of u comma v is 0 to this term, whatever the term is there, this term integral 0 to t e raised to minus 2 pi u of x naught of t plus v of y naught of t dt. Let us take this as h of u comma v, where the last step follows the f of u comma v. This one is independent, that's why we have taken outside. If the motion variable x naught of t and y naught of t are known, the transfer function h of u comma v can be obtained directly. Suppose that the image is undergone uniform linear motion in x direction only at a rate of x naught of t is equal to, here we have given x y direct only x direction, therefore y here is 0, x naught of t equal to at by t. When t is equal to capital T, the image has been replaced by total displacement of A, and y naught with y naught of t is equal to 0. So this will become y naught of t. So what we are taking, only in the x direction, y direction there is no displacement, therefore y naught of t is equal to 0, and A is equal to capital T, therefore x naught of t is equal to x naught of t is equal to at by t, where t we are taking as small t, we are taking as t, therefore substituting here t, we get displacement of A. Therefore the above equations, which h of u comma v, this equation h of u comma v, in this expression if you substitute y naught of 0, y naught of t as a 0 and x naught of t as a, we get here integral 0 to t e raised to minus 2 pi u of x naught of t dt. Now 0 to t u, where x naught of t we have taken at by t, therefore integrating this one we get t by pi ua sin pi ua of t e raised to minus j pi ua. Observe here h vanishes at a time at the values of u given by u is equal to n by a. N by, if you substitute u is equal to n by a, so that will become the sine pi multiples of sine, where n is an integral value, you can only integer, it can accept only integer values. If we allow the y component to vary as well with the motions given by y equal to bt by t, then the integrating function will become, so first we have taken only x direction, y direction 0. Now if we also allow the y direction to be variable, then h of u comma v is equal to t by, you can see the changes here, t by t, pi of ua, here pi of ua plus vb, here sin pi ua, here sin pi ua plus vb, here e raised to minus pi ua, here e raised to minus j pi ua plus vb. So this is the expression. Now you can see the image here, the second image, whatever the image is there, this is the image of blurred image. The second image is a blurred image by computing the Fourier transform of the whatever the function for first signal is there, multiplying the transform h of u comma v with and taking the inverse transform. The first figure is the original image, and this is the image by applying the motion modeling, mathematical modeling. So this is the way of estimating the degradation function using mathematical modeling. Thank you.